Happy Pi Day, everyone. All right, so here's our start. Thank you for watching the video. Send us a pie. What is it? What do you say? Like and subscribe. Send us a pie.
Smash that subscribe button.
We want to see Mr. Beamer's YouTube channel.
All right. What's that?
If you get 10,000 subscribers, can we pie you?
All right. So in general, can we find this thing, e to the at, where A is an n by n matrix, so that x equals, I need to write it in the other order so we can do the multiplication, e to the at times c is a solution to x prime equals ax, the system x prime equals ax. A is an n by n matrix, and C is an n by 1 column matrix of our arbitrary constants. That we would then solve for if we had an initial value problem. So this is our question. Can we define this matrix exponential function so that this quantity, e to the at times c, is a solution to that equation? So we need to make sense of this idea of what an exponential of a matrix would mean. Now, I want to point out we're not defining the matrix exponential in full detail. We're not going into all the mathematical details of the matrix exponential. We're just kind of touching on how we get started on the topic, put it that way. So what we're going to do, and I'm going to say recall, e to the at, the Maclaurin series expansion of the exponential function is 1 plus at plus at squared over 2 factorial plus at to the third over 3 factorial plus dot 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 plus a to the k t to the k over k factorial. And this, we can write this as the sum, k equals 0 to infinity, of a to the k, t to the k over k factorial. That's our power series expansion of the exponential function. And this converges for all t. So you can use the ratio test and show that the radius of convergence is infinite. So motivated by this, we're going to define e to the matrix at as this quantity equals the identity matrix instead of a 1 plus matrix A times t plus matrix A squared times t over 2 factorial plus matrix A to the third, so this should be t squared, t to the third over 3 factorial plus, and we get a to the k, t to the k over k factorial. And we could write this as the sum, k equals 0 to infinity, of a to the k, t to the k over k factorial. And probably second to assuming that our solution is an exponential function, assuming that writing something out as a power series expansion is probably the second most often used technique in math to get towards something that we're interested in. We can show this converges to an n by n matrix for all t. And a reminder, a squared just means a times a. A to the third is a times a squared, etc. So this is going to be, we're going to define our matrix exponential function in this way, and we're going to do a couple of operations here and talk about this, and then we'll show that this does, with this definition, this does in fact serve as a solution to that matrix differential equation. And just to, before we go on, we can, using this idea, we could define the sine of a matrix, or the cosine of a matrix, or any other function of a matrix by using the power series expansion for that particular function with a matrix here instead of a constant. So we only have a little bit, there's only a few problems that we're doing in this section for homework, but I'm going to post this on our Schoology page, well-known power series, because we'll need to recognize some power series when we do these. These are the most, the ones that come up the most. Exponential, trig functions. This one is a geometric series, and the inverse tangent is a really nice one because you can do a lot of stuff with the inverse tangent. Well, these are all just Taylor series. Well, these are Maclaurin series expansions that you construct with the derivatives of the functions. So all that stuff that you did with Taylor series. The inverse tangent actually comes from this, and then you substitute an x squared for this quantity, a minus x squared for this quantity, and then you can integrate and you get the inverse tangent power series. So there's different manipulations you can do once you know some power series to come up with other power series, which is kind of nice. So I'll post this on our Schoology page, and I'll keep this up because we're going to need it here in a second. So let's look at an example. We're going to find e to the at for a equals 0, 1, 1, 0. So for 2 by 2 matrices, we should be able to do this, do a couple of multiplications by hand. If you have to multiply, I think there's one homework problem where it's a 3 by 3 matrix. Use technology for that to do the a squared and a to the third. So here, a squared is 0, 1, 1, 0 times 0, 1, 1, 0. So we have 0 times 0, first row times the first column, 0 times 0, plus 1 times 1, you get a 1. First row, second column, 0 times 1, plus 1 times 0, 0. Second row, first column, 1 times 0, 0 times 1. Second row, second column, 1 times 1, 0 times 0. And this is the identity matrix. So a to the third is a times the identity matrix. So that's going to be 0, 1, 1, 0 times the identity matrix, which we know is just 0, 1, 1, 0, which is a. I forgot I wrote a 1 there instead of a 0. That is a. Any matrix times the identity matrix is the matrix we start with. And we can see then that a to the fourth is this times a, which is the identity matrix. A to the fifth is going to be a. So we can write that a to the k in this case is the identity matrix for k equals 2, 4, 6, and it equals a for k, for odd k, 1, 3, 5, 7, etc. So e to the at is our definition, I plus at plus a squared t squared over 2 factorial plus dot dot dot. So for our case, that is I plus at plus a squared is I t squared over 2 factorial plus a to the third, which is a t to the third over 3 factorial plus our next term is going to be I t to the fourth over 4 factorial, and we can keep going that way. I'm going to separate these out, all the terms that have a's in them and all the terms that have i's in them. I'm going to write separately. Yes?
Are we always doing infinite with power zero? Like, how do you know when to stop?
We stop, so you write enough terms to recognize a pattern. Usually it's going to be, after 3 or 4 terms, you're going to be able to see the pattern. So I'm going to separate this out into terms with I in them and terms with a in them. I'm going to factor out that identity matrix and the a matrix. T squared over 2 factorial plus t to the fourth over 4 factorial plus t to the sixth over 6 factorial plus dot 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 plus a times t plus t to the third over 3 factorial plus t to the fifth over 5 factorial plus dot dot dot. And both of these are common power series. This equals I times, let's look at our handy dandy little sheet here. So we have t squared over 2 factorial, t to the fourth over 4 factorial. That is a cosh. Yes?
Don't you need a 1?
Did I miss an I?
Yeah, because there's just no 1.
Oh yes, I missed a 1 there. This should be a 1 plus. So that's a cosh. So this is cosh t, and this is plus a, and this one is a sinh. And so e to the at, if I write it in matrix form, is going to be cosh t, sinh t, sinh t, cosh t. I get coshes on the main diagonal and cinches on the other diagonal, because our I is here and A is there. So I have a 2 by 2 matrix. That is e to the at. So our goal here when we find our matrix exponential is write out a few terms so that you can then hopefully recognize the form of that power series and match it to a common power series. Isn't that fun? So
I think I misunderstood power series.
e to the at is, in this case, e to the power of this matrix is this matrix. Yes.
How did we get like our first I? Is that like usually like, or is that usually like the zero? Is that always the like the matrix?
This one?
Yeah.
Yeah.
Okay, so like anything to the zero is that any matrix or just this?
I'm sorry?
Like anything is it any matrix to zero is the identity matrix?
The identity matrix. Yeah.
Okay.
Like any number to the 0 power is 1.
Okay.
All right, so let's go a little further here. Now, there's certain kinds of matrices where our matrix exponential is a little nicer. For a diagonal matrix, maybe not a little nicer, a little easier to find. For a diagonal matrix, and a diagonal matrix is a matrix with numbers on the diagonal and zeros everywhere else. So we just have numbers on the main diagonal. E to the at in this case, or e to the at, we'll say, is e a11 t 0 0 0 e to the a22 t 0, and then here we get e to the a sub n n t. So for a diagonal matrix, our matrix exponential is just each element exponentiated. Unfortunately, our matrix in the last example was not a diagonal matrix because we had numbers on the secondary diagonal. So now let's look at the derivative of e to the at. Is we're going to take the derivative with respect to time, e to the at, which is the derivative of I plus at plus a squared t squared over 2 factorial. I'll write one more, a to the third t to the third over 3 factorial plus dot 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 plus a to the k t to the k over k factorial. And we differentiate term by term. Well, the derivative, the identity matrix, is a matrix full of constants. So derivative of that is 0. Derivative of at is just a. Derivative of at squared over 2 factorial, we bring down the 2. That cancels with the 2 factorial. And we get a squared t. Plus, when we take the derivative here, this 3 comes down, cancels the 3 in the denominator. So we get a squared t squared over 2 factorial. Plus here we would get a to the third t to the third over 3 factorial plus dot dot dot. I'm going to factor out an a. And this is just a e to the at. Let's see, a, this should be, what did I do wrong here? I did a squared twice. This term, what did I do? This should be a.
No, that should be squared.
Yeah, this should be my third.
No, t squared
Ah, yes, a to the third. T squared, yes. T squared over 2 factorial. This should be a to the fourth. T to the third over 3 factorial. There we go. Now we can factor out the a, and I have it written down correctly. And our derivative is a e to the at.
Please scroll again.
What's that?
Please scroll again.
And now we can see if x equals e to the at times c, the derivative with respect to time of e to the at times c, where c is a column matrix, equals a e to the at times c, which equals a e to the at times c, which equals a times x. So, times c. That's right. So x equals e to the at times c is a solution to x prime equals ax. So in our previous example, for a equals 0, 1, 1, 0, e to the at was cos t, sinh t, sinh t, cos t. X equals cos t, sinh t, cos t, times C1, C2, which is, oops, I forgot my H here, C1 cos t, C2 sinh t, C1 sinh t, C2 cos t. Is a solution to x prime equals ax. And you can verify this by writing the characteristic polynomial, finding the eigenvalues, finding the eigenvectors. Because you have sinh and coshes, you're going to get exponential solutions here. This is an alternate way to solve these equations by finding the matrix exponential. And given our definition of e to the at, it's not difficult to see that it is a fundamental matrix of the system. So my goal here was to introduce us to this idea. And my hope is that when we do the next unit, when we talk about Laplace transform, we can come and revisit this because we can use the matrix exponential and then the Laplace transform to solve systems of differential equations using the matrix exponential. And the matrix exponential allows us to solve non-homogeneous systems using the Laplace transform instead of undetermined coefficients or variation parameters. Yes?
But so can we only do this if like a squared and a cubed like they give a pattern when you multiply to each other? Because like otherwise how do you calculate it?
I'll say for what we are going to do, they will give a pattern. I mean, we could still do it, but then we would have, we could still use what we get, but we'd have the entries in our matrices would be power series, so we'd get approximations to our solutions. But for nice matrices, usually the matrix exponential turns out to be something kind of nice. It's harder if it's like, if your matrix exponential gives you like sums or products of some of those functions. That's when it gets a little trickier. All right, questions? So our homework is just, we have a few where we're just finding the matrix exponential given a matrix, and one, I think, where we use the matrix exponential to solve a system of equations, which is just, again, finding the matrix exponential given the matrix. And it's all going to come down to doing that multiplication and then recognizing your entries as some common power series.